Next, I want to talk about the intuitions of the dot product. So technically, the dot product measures how similar or how well two vectors travel together. I have some scenarios here. I have a two vector u and v, and in the first case, u and v are pointing in the same directions. In the second case, you have u and v pointing in completely opposite directions. In the third case, u and v point in kind of similar directions. And the last case is where u and v pointing in the opposite direction, but not exactly the opposite directions. So again, the dot product measures how similar or how well two vectors u and v travel together. If u and v point in the exactly same directions, then the angle between the two vectors is 0. So therefore, the dot product is u dot with v equal to the magnitude of u times the magnitude of v, because theta equal to 0, implying that cosine of 0 is equal to 1. Therefore, the dot product is equal to the product of the magnitude of u and the magnitude of v. If u and v point in the exactly opposite directions, then the angle between the two vectors is 180 degrees, and cosine of 180 degrees is negative 1. Therefore, you have u dot with v equal to negative of the magnitude of u times the magnitude of v. These two cases implies that the two vectors are parallel with one another. It doesn't matter the directions, u and v are parallel. If u dot with v greater than 0, then u and v form an acute angle. When u dot with v less than 0, then u and v form an obtuse angle. And we already learned that if the two vectors are perpendicular or orthogonal, or intuitively they do not travel well together at all, the dot product will be 0. So this is the intuitions of the dot product. So dot product in a way give you the idea of how to calculate the angle between the two vectors, or in other words, give you the idea of how similar or how well the two vectors travel together. Now let's move on to the last topic in this lecture, which is the projections of one vector onto another vector. So consider two vectors u and v with the same initial point. Then you have the two formulas. One is the scalar projections of v onto u and the vector projections of v onto u. So what I'm going to do is I'm going to write down the formula first, and then I'm going to show you where's the formula actually coming from. Okay, so for the scalar projections, of v onto u, this is denoted at components, so written as COMP of v onto u is equal to the dot product of u dot with v divided by the magnitude of u. And for the vector projections, this is denoted as prods, PROJ of v onto u is equal to whatever you get for the scalar projection. So this gives you a scale. You apply this scale on the unit vector. Right, so now I'm going to show you where's the formula coming from. So again, consider the two vectors, vector u and vector v, and they have the same initial point, which is p in this case. So you want to project the vector v onto the vector u. This is the vector projections that we're going to obtain. And this is prod of v onto u. In another scenario, if you have the two vectors pointing in this particular directions, And again, you have the vector v, and this is the vector u, and v is projected onto u. Then the arrow in red is the projections vector of v onto u. And when you project a vector onto another vector, obviously you have another vector, and this vector projections, when you measure the distance or the magnitude of the vector projections, you have the scalar projections. And that scalar projections, again, is just distance or the magnitude of the vector. So this I call x, and this x is equal to the scalar projections of v onto u. Let's derive the formula of the vector projections and scalar projections. So here I'm going to make the assumptions that theta is the angle between the two vectors u and v. And I'm going to say that x right here is the magnitude of the vector projections. So let theta be the angle between u and v. Then cosine of theta, which is the adjacent over the hypotenuse, that is x over the magnitude of v. So again, this is the right triangle. X is the magnitude of the vector projections, and here is vector v, so the magnitude of the hypotenuse is the magnitude of v. And you can solve for x from here. So x is equal to the magnitude of v times cosine of theta. But by the dot product, cosine of theta is equal to u dot with v divided by the magnitude of u times the magnitude of v. And then we can substitute this information into this equation, and we get x equal to the magnitude of v times u dot with v over the magnitude of u times the magnitude of v. So obviously we can make the cancellation for the magnitude of v, and we left with just u dot with v divided by the magnitude of u. So this is the scalar projections, right, or the distance or the magnitude of the vector projections. And by convention, this is the notation for the scalar projections. So com of v on to u. Now we just derived the scalar projections, and for the vector projections, so vector projections of v onto u has the same direction as u. Then we have that projections vector of v onto u is equal to u dot with v divided by the magnitude of u, because you want to have vector projections pointing in the same direction as u, so you multiply this with the unit vector u. So this is a scalar apply, or a scale apply on the unit vector u. So that is scalar projections, that is vector projections. Now we're going to apply this formula to the following example. So we want to find the vector projections of v onto u of two vectors, 3, 5, 1 and negative 1, 4, and 3. So the projections vector is, so the projection vector of v onto u is again equal to u dot with v divided by the magnitude of u times the unit vector u. So here's the few calculations that you want to do. First, I want to calculate dot product between the two vectors, and then I want to do the magnitude of u. So the dot product between the two vectors is 3, 5, 1, dot with negative 1, 4, 3. This is equal to 3 times negative 1 plus 5 times 4 plus 1 times 3. And if you do the calculations correctly, it's going to give you 20. Now for the magnitude of u, you have square root of negative 1 square plus 4 square plus 3 square. And again, if you do the calculations correctly, you get square root of 26. You're going to substitute this information into our formula, and you get the dot product is 20 over root 26 times, this is the regular multiplications, vector u, which is negative 1, 4, 3 divided by root 26, or I get 20 over 26 times negative 1, 4, 3. I mean, you can stop right here, or you can go a little bit further into simplified the vector projections. And if you do the calculations correctly, you're going to get negative 10 over 13, 40 over 13, comma 30 over 13. Similarly, I'm going to apply the vector projections formula to two-dimensional vector. And here again, you want to do the scalar. You want to do vector projections of v onto u. So projections of v onto u is equal to u dot with v divided by the magnitude of u times the unit vector of u. Again, you want to do some calculation in advance here, so you want to do the dot product of u and v, and then the magnitude of u. So u dot with v equal to 3, negative 2, dot with 1, 6, or 3 times 1 plus negative 2 times 6. This gives you negative 9. And the magnitude of u is square root of 1 square plus 6 square. This is equal to square root of 37. So you substitute this information to our formula. You get u dot with v is negative 9 divided by root 37 times, this is regular multiplications of 1, 6 divided by root 37, or you have negative 9 over 37 times 1, 6. Well, you can leave it like that if you want. Or you can distribute scalar into the vector. You get, this is negative 9 over 37, negative 54 over 37. Now for the last example in this lecture, we're going to find the vector projections of u onto v and the scalar projections of u onto v. So you have to be careful in this case when you calculate the projections vector and the scalar projections, because it's no longer v onto u, but this case, this is u onto v. So for the scalar projections of u onto v, this is equal to v dot with u divided by the magnitude of v. So as you can see, the formula gets switched out a little bit. So instead of divided by the magnitude of u, now you divide it by the magnitude of v. So u dot with v is 3, 4 dot with 4, 1. And the magnitude of v is 3 square plus 4 square. What you get on the numerator is 12 plus 4 divided by square root of 9 plus 16. Right, so you have 16 over root 25, or 16 over 5. And now for the projections vector of u onto v, you have v dot with u divided by the magnitude of v, multiply with the unit vector of v. So this part of the formula we already calculate, which give you 16 over 5. You multiply with v. Again, this is regular multiplication. V is 3, 4. And the magnitude of v is 5. So you get 16 over 25 times 3, 4. Alright, so that's it for me for this lecture. Please let me know if you have any questions. Thank you.